Okay, good morning. Welcome to
FamilyMath1178.
FamilyMath1178. So thanks to Amy Hogan, this morning I sort of remembered or was reminded about a really cool video that Grant Sanderson did a couple of years ago. I think it was 2017 on the fair division problem, and specifically about if you have a necklace that has some jewels in it, how many cuts do you have to make to split the jewels evenly?
Yep.
So you watched this video, and why don't you write down like a couple of things that you thought were interesting in the video.
Okay, so I thought the actual problem itself was pretty interesting. So I think it was called the stolen necklace problem.
Yep.
And then...
Alright, so the problem itself is pretty interesting. And how do you say that problem?
Okay, so you have some different types of jewels. In this example we have two, the green and orange. And they're on a necklace. And your goal is to divide up the jewels between you and a friend, between you, and then so that you each have the same number of jewels, but making as few cuts in the necklace as possible. And then the theory is that with n different types of jewels, you can do it in n cuts.
Yeah, so in this case, the other condition is you need to have an even number of jewels.
So you can actually split them evenly.
Yeah, so in this case, we should be able to do it with 2 cuts, and we have 2, 4, 6 orange ones, and 2, 4, 6. So we should be able to split it 3 and 3 with 2 cuts.
I think actually we can do it in just 1 cut, actually. Just cutting here.
Okay.
We can do it in 1.
Alright, so in this example actually we could do it with 1 cut, but maybe there's a more complicated arrangement where there isn't a way to do it with 1 cut, but we'll see. We'll explore that in the next video.
And then the video talked about how this relates to the Borsig-Ulam theorem, but I don't know how to spell Borsig-Ulam.
Alright, maybe you could just abbreviate it BS.
BU theorem?
Is that better than BS?
Probably.
Borsig-Ulam.
Yeah.
The BU theorem.
Okay.
So the Borsig-Ulam theorem says what?
So it seems wildly different to this problem. It says that if you have a sphere in the 3D plane, you can, if you somehow squish that sphere down somehow into the 2D plane, and not break the sphere at all, there will be 2 points that were opposite each other on the sphere, that were antipodal points, that end up on top of each other in the 2-dimensional plane, in the same spot.
Yep. Yeah, so it's really cool. So if you have, I should have grabbed a sphere ahead of time, but we did not, which is fine. But we could pretend one of these cubes was a sphere. So you have a sphere, and you somehow, in a continuous way, it just means you don't sort of tear it or anything.
Yeah. I guess sort of an example of that would be looking on the, so if you were to cut it in half and looking on that line around the sphere and then sort of just squishing it.
Yeah, just squishing it down.
That.
But you can also sort of stretch it and squish it down. And,
yeah.
But there will always be 2 points.
Yes.
That were originally on opposite sides of the diameter that end up on top of each other.
Yes.
So that's cool. So that's an interesting theorem, and it has a name. So it was a big achievement to prove it, and it's called the Borsig-Ulam theorem. But that seems to be a theorem about spheres, and it's a really interesting and probably pretty surprising statement in the video that it is actually connected to this jewel problem.
Yes.
All right. Was there anything else that caught your eye?
That was the main point of the video, that these 2 things were connected.
Okay. Well, cool. Let's see if we can do some examples in the next videos of finding these divisions.
All right.